So hello everyone. Today we are solving another question on LeetCode. The name of the question is recover a tree from pre-order traversal. This is a hard question and this is also the LeetCode daily question for today. So let's just see what the question is asking us to do. Then we can go into the approach and the code to understand better. Okay. Now let's start with the question. So we run a pre-order depth first search DFS on the root of a binary tree. So basically we have a binary tree and we are running a DFS on it. And at each node in the traversal we output D dashes. Okay, where D is the depth of the node, and then we output the value of the node. So what we are doing is that we are outputting some dashes that is representing the depth of the node, and then you are outputting the value of the node. Okay, if the depth of the node is D, the depth of its immediate child is D plus 1, and that's obvious. If you have a node that is at depth D, its child is going to be at the depth of D plus 1. Okay, and the depth of the root is considered as 0. So whatever is the root, we are assuming that its depth be 0. So we are starting from depth 0 and not depth 1. Okay. So what the question is asking us to do is that given the output traversal of this traversal, recover the tree and return its root. So if you see, for example, in this case, this kind of an input is given. This is representing the traversal uh, of the tree, and from this traversal we want to find out the original tree, and this is based on the pre-order DFS. What is pre-order DFS we are going to see. And also one more thing that has been mentioned is that if a node has only one child, the child is guaranteed to be the left child. Let's assume that you have some case where let's say the input string is something of this form. So in this case, because this one has only one child, we are going to assume that it's going to be the left child and it's not going to be the right child. Okay. Now let's see the example more to understand. Okay. So the example we have over here is this one. So you have this node, that one. It will be at depth 0. These all will be at depth 1. This will be at depth 2. Okay. And now let's see the pre-order traversal. What happens in pre-order traversal? So the pre-order traversal uh, tells that when you are traversing the tree in a recursive fashion, what you do is that you first visit the root of the tree, and once you have visited the root of the tree, then do the pre-order traversal for the left child, and then once the left child pre-order traversal is done, then you do the pre-order traversal of the right child. So it's a recursive way in which you do. So basically you go to the root, then you go to the left part of the subtree, and then you go to the right part of the subtree. So you can remember, because it is pre-order, the root comes first before the left or right. If it is an in-order traversal, it's going to be left, then you have the root, and then you have the right. And if it is a post-order traversal, it will be left, right, and then you have the root. Okay. Now let's see how the output is given, and we can see how to solve this kind of question. Okay. Now let's see how this traversal has happened. So first what would have happened is that we would have come to the root part. So once you come to the root part, you know the value is 1. So we output a 1. Okay. And what is its depth? Its depth is 0. So you don't have any dashes. Okay. Then once you have went to the root, you want to go to the left part. So from 0, you go to the left part. So the left part is 2. So you are going to output 2, but the 2 is at a depth of 1. So you are going to output 1 dash before it. Okay. Then you go to 3. Then once you go to 3, it is at a depth of 2. So it's going to return 2 dashes for the depth and the 3. And then you're going to return back. Then you're going to go to the right because you went to the root. Then you went to the left. Then you are going to go to the right part. So right part is going to be 4. That will also again be at a depth of 4, depth of 2. Then you are going to return back. So its traversal is done. So this is also going to return. Now we will be going to the right part of the 1. So once you go to the right part, you're getting 5. 5 is a depth of 1. So I output a 5. Then I go to the left subtree. It's a 6 at a depth of 2. And then I return back. And then I go to 7. That is also at a depth of 2. So I put 2 dashes for the depth, and then I output the 7. Then I'm going to return back, and then I'm going to return back, and finally I can return out. So this way you can say the output string that we got was 1 dash 2 double dash 3 double dash 4 single dash 5 double dash 6 and double dash 7. So I hope you understood how we are traversing, and this string has been given. And what you are asked to do is that, hey, you are given the string. Now tell me what was the original tree, and so recover the original tree from this serialized string, and once you recover it, please return it. Okay, I'm just clearing it. And one more thing, like before we continue, let's just try to see this string. So whenever you have a number, you can count the dashes before it to get the depth. And whenever you have a number, it's not supposed to be it's not exactly the number, it's the character representation of the number value. So basically, instead of 6, if this was a 67, we have to take care of this also, because in a string, it's going to be a sequence of six, the character 6 and then the character 7, but we want to consider this as whole 67. So before we like try to solve the question, now let's see how we can convert this string into a meaningful format, which will be more easy to understand. As you can see over here, you have 1 dash 2, the same example. So what I'm doing is that I want to output this, like convert it into such a form, such that I have it in this kind of a form where it is easier to understand. Here the left part of the values, if you see, these are all representing the depth, and the right part is representing the value of the node. So if you see, it's node 1. Node 1 is at a depth of 0. Let's take this one. So node 4 is at a depth of 2. As you can see, node 4 is at a depth of 2. This is 0, this is 1, and this is 2. And similarly, if you consider this node, for example, so you have node 7 at a depth of 2. So that is how I want to convert the string into there. So once I have this kind of a data, it is easier for me to work on this. Now let's see the code that is converting this the serialized string into this kind of a format. Okay, let's go to that part of the code and see how this is working. Okay, so if you see, if you see the example over here, I'm gonna come over here. Okay, so what I'm doing is that I am telling that, hey, I don't want to deal with the string. Let me consider a list of nodes where every node will be represented by the depth of it and the value of it. Okay, so I'm creating a vector pair of int comma int, and I'm calling it VP for vector pair. Okay, now what we can do is that let's traverse the string. Let's see if it's a dash. If it's a dash, I'm gonna add it to the dash, let the depth. So if it's a depth, if it's a dash, I'm gonna add it to the depth. And if in the case if it's a digit, let's say it is like for example, you have a sequence like this 56, and we get a digit. I know that whatever, because it's a digit, this is going to be contribute to the value of the node. So let me add it to the value. So that is how the code is working. Now let's go to the code and see how this is working. Okay, so what I'm doing is that I am iterating through the string, and I'm extracting the character. So first thing what I do is that I check, hey, is the character I got, is it a digit or is it a dash? Okay, for example, if like as you can see in this example, that let's assume that it is a digit. So if it is a digit, I know that this is going to contribute to the value of the node and not to the depth of the node. Okay, and before we do that, we have initialized value d representing the depth, and we have the value val representing the value of the node that we're considering. Okay, and because this is a digit, I know that it's going to contribute to my value. So let's say it was something like 34. Let's say we got 3. So what we can do is that we can multiply value with 10. So initial value is 0. So 0 into 10 is 0. And then we are going to add the value of this character in the integer format, that is ch minus 0. So we are going to add 3. So now my value becomes 3. And once that is done, the next character that we are going to get is the character 4. And once you go to character 4, you know that this 3 must have been shifted by one's place to the left in my decimal representation. So what I'm doing is that I'm multiplying value with 10. So now this value becomes 30, and to it I add this 4. So I add a 4 to it, and my value becomes 34. So this way you can see I'm able to get the value of the node, and that is how the code is working. Okay, but what do we do if in the case we find out that the character that we were dealing with is a dash? So if it is a dash, what we can do is that like for example, let's consider this one. If you see this dash over here, let's assume we are currently getting this dash. You know that this dash is going to add to my depth. If my depth value at the current situation is 1, then it's going to increase that to 2. So what I've done is that if I'm getting a dash, let me check the previous character to it. If the previous character to this dash is also a dash, that means this is only going to help in the depth. So that's why I'm doing d plus plus. So I'm increasing the depth. But okay, let's assume that we got this dash that is occurring for the first time after a number is done. So in that case, we know that our value must be having the value of the node, and the d will be having the depth of the node. Because we already have calculated that in the previous iteration, what we can do is that we can simply push back this value, the d, depth, and the value into my vector pair. And once I have done that, I'm gonna have to edit the values, right? Because the value I just updated, I'll update the value to 0, because I want the value to be reset to 0, so that the other numbers which are going to come, we can use it use it accordingly. And I'm going to set the depth as 1, because this is representing the first dash that we got. So that's why the depth at the current moment is going to become 1. Okay, and once you do that, you can just come out of the loop. And what I've done is that what was happening was the last depth, the last node value and the last depth was not being added because we were exiting out of the loop. What we can do is that we can just simply add it. That is what I've done. It depends upon your implementation. Okay, and I've just outputted the value, that how the output is coming. And if you can see over here, we have all the node values on the right, and we have the corresponding depth value on the left. In this example also, if you see, you can see, let's say you take the node 4. So node 4 is at a depth of 3, is what this is what the output is coming. So once we have done that, now let's see how we can use this values. This is a representation of the depth and the node val. How can we generate the original tree, recover the original tree from this representation? Okay, now let's take one of this example and then try to see how we can do that. So if you look at this example, 1 2 3 4 5 6 7, its representation is same as this one, 1 2 3 4 5 6 7 with the appropriate number of dashes. So its representation something like 1 is at a depth of 0, 2 is at a depth of 1, and so on and so forth. Okay, so whenever you see a question involving trees, the first approach that you can go think is that, hey, can I use a recursion somehow to generate the original tree or solve this question? Okay, now let's see, like the algorithm that we are going to devise is that, okay, we know that the first node, whatever is there, will be at a depth of 0. So we can think of a recursive function that is going to take these values as the input, this VP, the vector pair array, and the depth and the current depth of the node, because it's the starting of the tree, the current depth is going to be 0. And what the recursion function is going to do is that it's going to create the root node at that appropriate depth level, and then it is recursively going to call, hey, recover the subtree for the left part and recover the subtree for the right part. Do that and return me the whole tree. And then once that is done, you can just simply return the root that has the appropriate root node and the left and right part of the subtree. Okay, now let's see how we can do that. So in the example, if you can see, we first have 1, that is a depth of 0. Okay, so when you're first entering, you're gonna get this node, so that is the depth of 0. So you're going to create a node of value 1 that is at a depth of 0. Let's just assume this is at the depth of 0. And once I've done that, I can skip this node, that, hey, your work is done. Now the next node that we are going to consider is going to be the left part of the subtree, because you know, in the pre-order traversal, as I said, you first go to the root, then you go to the left, then you go to the right. So because this was a depth of 0, I know its child will be at a depth of 1. So I'm going to ask the function, hey, can you check if there is any node of depth 1? If there is, then it's going to be my left child. Okay, and we can see that, hey, 2 is there. So I'm going to consume this node and I'm going to add the value as 2. Then what I'm going to do is that I'm again going to go to the left, because it's a recursive function. Once you are done with the root, you are keep on going to the left as long as you can go. Then you will go to the right, and then you can continue this in a recursive function. Okay, I came to 2. Then I'm going to ask, hey, do you have any child for 2 at depth of 2, because its depth was 1, its depth was 0, its child will be at depth of 2. So at depth of 2, we have the node 3. Okay, so we added 3. Then we're going to go to the left, and its child depth will be 3. So we have that. So I'm going to add 4. Then what I'm going to do is that I'm going to go to the left of 4, and I'm going to ask, hey, is there any node at a depth of 4, because its depth was 3? And you can see there is nothing at a depth of 4. Like the next node is not at a depth of 4. So what we can do is that we can assign it as a null, that it does not have a child, so it will be null. Then we are going to go for the right part. Right part also, its child depth will be 4. We don't have it, so this will again be null. So we can just return back. And once we return back, we got the 3. I am going to go check at the right of 3. Okay, what should be at the right of 3? Like its depth value. Its depth value, this 4 also we had consumed, so I'm going to cancel that. At the right of 3, we want something that is at the depth of 3, that is the current depth plus 1. We don't have anything at the depth of 3, so I'm gonna set it as null, and I'm gonna return back. Then we came back to 2. So is there anything like any child that we can use for 2 that is at a depth of 1 plus 1, that is 2? So we don't have that, so this will again be null. Then we return back to this one. Then once we return back to this one, you want to check, hey, can it have a right subtree with a depth of 1? Like, can you generate that? And we see this, there is a node which is at a depth of 1. So hence this will be the value for our node. So this will be 5. So we got something. Then we are going to go to the left. If you see, at every point we visited the root, then we went to the left. Once we could not go further to the left, we went to the right. And once we return back, we went to the right. But once you again come to this position, this is again becoming the root. So we visited the root. Now we again want to go to its left. So for the left of 5, what should be the depth? Its depth should be 2. Do we have something, this was consumed. So do we have something that is at a depth of 2? Yes, we have a 6. So I'm going to consume the 6 and I'm going to erase this one. Okay, now I'm going to go to the left of the 6. Is there anything that is at a depth of 3 because the parent node was a depth of 2? Okay, we have a 7. So I'm going to go to the 7. Okay, and if you see at this current situation, all my nodes are consumed. So all the other child are going to be null. But let's just assume I just want to continue. Hey, is there anything on the left of 7? No, there is nothing. So it's going to be a null. Is there anything on the right of 7? No, there is nothing. It's going to be a null. For 6 also it's null because we don't have any more nodes to take care of. And once we return, what will be on the right of 5? It is a null. So if you see, by following this method, we were able to generate the tree that was 1, 2, 3, 4, and 5, 6, 7. And every time you are done with a root, you can go to the left, and then once everything is done for the left part of the subtree, you can try to go for the right part of the subtree. And in the case if all the nodes are consumed, you can just return null, that we don't like, there is no child that is possible with that depth. Or if you're explicitly asked here, like for example in this case 2, is there any child with depth of 2? And you don't find a node, so you can just simply return null, because whatever node you have, it's not for the child of 2, it's for some other node, so you can just return a null. Okay, and the similar approach we can follow for the other examples if you also want to check. So let's just quickly go to this one. So I have a 1. Okay, I'm done with 1. Okay. Do I have anything on the left that is at the depth of 1? So for the depth of 1, I have 401. So I set up 401. Okay. So 401 is at the depth of 1. Is there anything on the left of 401 that is at the depth of 2? Yes, we have 349. So we are done with 349. Is there anything on the left of 349 that is the depth of 3? Because this was the depth of 2. Yes, we have a 90. So I'm done with 90. Is there anything on the left of 90 that is a depth of 4? Nothing. On the right of 90, nothing. On the right of 349 with a depth of 3, we don't have nothing. So we return back. Now we come back to 401. Its left part is done. That is at the depth of 2. Now if we go to the right part, its child depth is also going to be 2. So we are going to check, hey, is there any node with a depth of 2? It's going to be 88. So we are going to set it as 88. And once you're done, we have already exhausted all the string, like all the characters in the string. So in that manner, you can say that we have already generated the tree. And if you see the tree example, it's this 1, 401, 349, 90, 88. So this is the tree that we have, and this is matching this one. So now let's go to the code. Let's check the recursive logic and how this is working. Okay, and let's come to the coding part. Okay, so once you can see, like I explained to this part of the code where we are converting the string, the serialized string into in this kind of a format where we have the depth and the value of the node. Once we are done with that, I'm creating a node. Node is representing the current node that I want to consider. Like this is the 0th node I want to consider, this is the next node that I want to consider, first node, second node, third node, and so on and so forth. So here node is representing the node that I want to consider in my vector pair. Okay, once you have that, I'm creating my tree node answer. So this will be the final recovered tree that I want to return. So I'm calling this function recursive function recover. I'm passing in the vector pair, this vector pair list that is having the depth and the node value, and I'm passing it the current depth of the tree node that I'm expecting, because because this is the starting part and the first node that we encounter has a depth of 0. So I'm giving it a depth of 0. I'm saying that, hey, consider this tree, recover the tree and give it to me, and the first node is supposed to be at a depth of 0 because I'm just starting. So I have passed in the depth. So the recover function is taking two values, that is the vector pair of list and the depth of the node that we want to recover. Okay, and once you have done, once you're going to start that, we are going to go in recursive function. So whenever you have a recursive function, you think of two or three approaches. So first thing is, what you do is that you think of a base condition. The base condition is the basic condition that you're going to you're going to handle, and you can return in the value. And once you think for the base condition, once the base condition is done, you can write the recursive logic. And once you can form the recursive logic, you can go for the third thing, that is you can just return the final answer that you require once the recursive logic part is done. So whenever you're writing a recursive question, you need to think of this condition. So what could be the base condition, the most simplest condition? The most simplest condition is that, hey, if I have exhausted all my nodes are exhausted, then I have no more nodes to consider. So I can't create any subtree or recover any subtree. So in that case, if I've already consumed all the nodes, just return a null. Hey, I've consumed all the nodes. Okay. What is the other base case that we can think of? Okay, let's assume that we are asked, hey, give like for example, we are currently at this node, and we are asked, hey, return, like create a tree, recover the tree from here, whose depth is supposed to be at a depth of 3, but we know that the depth that we have at the current moment is 2. So we know that we can't create or recover a tree at a depth of 3 if the node that we want to consider is of depth of 2. So what you can do is that, hey, if the depth that you want to recover is not matching the depth of the node that we have to consider in our vector pair list, then you can simply return a null. So these are the base conditions you can think. So we can check if the depth is matching to the node or not. That is one. And the second thing is that, hey, have we consumed all the nodes? If that is once done, we know that whatever value we have at this current position, that is the value of the root node that we're trying to recover. So what I can do is that I'm creating a new root node. I'm creating a root node, and what will be its value? Its value is going to be whatever is the value of the node that we are pointing to. So that's why I've initialized with VP of node. Node is representing the node that we're considering, and it's from our vector pair list. And the second value is storing the value. So I'm creating a new root node. I'm setting its value as the val, and once I have done that, I'm doing node plus plus that, hey, I have consumed this node, so I'm gonna skip that. And once I've done that, I want to recover the left part and the right part. So you can see it's going in the format. I'm going to the root, then I'm trying to recover for the left, and then I'm trying to recover for the right. And this is what is the pre-order DFS way that we are following. So what I'm doing is that, hey, my roots work is done. Now please recover the left subtree of the root if it can exist, and if it is existing, what should be the depth of the left part of the child? Given that the depth of the root node was d, so it will be d plus 1 as obvious. So I'm passing in here recover the left part of the child if with the depth of d plus 1. And once you're done with that, you're going to ask, hey, my left subtree is already recovered. Now let me see from whatever nodes I have, can I try to use that to create the right part of the subtree? If the depth is going to be present in the node, then it's going to help me. So what I did was that I did root left is equal to recover VP and d plus 1. And once it's done, recover the right part, that is root right is equal to recover the vector pair list, and the depth of the right part of the child is going to be d plus 1. And once you're done with that, you can assume that, hey, I have my root, okay, it's done. I have the left part of the subtree, whatever is to be in the left part of the subtree is done, and whatever is that they are supposed to be in the right part of the subtree is also done. So because I've done the root left and right, everything is done. I can just simply return back this root, and that is what I've done. And yes, this much is the part of the code that we were supposed to solve. And now let's see, try to run this example. I'm gonna hide this part. This is the standard C out part. I'm just gonna hide it. Let's run it. So if you see, yes, the example, the code is getting accepted. So now let me try to submit it. As you can see, this code is very fast. It beats 100% of the code. And if you see, let's talk about the time compression and space complexity. What we did was that first we took a O of n time, that is depending on the length of the string, to convert this into a vector pair, where we are having all the node values and the depth values. And that part is going to take a O of n space also, because we will be having some n number of nodes and the depth. So that data structure is going to take O of n space. And once you're done with that part, you are just running a recursive function. So recursive function, what it's going to do is that it's going to run on all part of the tree nodes. So overall time complexity is going to be O of n, where n is representing the number of nodes for the recovery part, and the initial conversion is going to be dependent upon the O of length of the string, the serialized string. So that's the overall time complexity, and it is quite efficient as you have seen. And also I wanted to say is that this code, if you want to go to the code, exactly the code that I've written, it's there in the description. And guys, please suggest what more questions you want to see, and if you have any suggestions for me, and like, share, and subscribe. And I hope you guys have a very nice time.